So, good morning, students. Let us discuss today in the series of video lectures on the subject electrical measurement and instrumentation. We shall discuss today the permanent magnet moving coil, that is the PMMC instrument. It is the one of the most accurate type of the instrument used mainly for DC measurement. That is a permanent magnet moving coil. As the name suggests, it has a permanent magnet and a coil which is moving. That's why the name is moving coil. So let us see the construction first. A permanent magnet is used in this type of the instrument. That's why the name permanent magnet. The aluminum former is provided in the cylindrical in between the two poles of the permanent magnet. So there will be the N pole and S pole, and in between that pole there will be a aluminum former, and coils are wound on the aluminum former which is connected with the spindle. Else before also we have discussed about the spindle. This spindle is supported with the jolt bearings. Two springs are attached on the either end of the spindle, upper end and lower end. The terminal of the moving coils are connected to the spring. Therefore, the current flows through the spring 1, moving coil, and the spring 2, because the spring and the moving coil, these two springs, one in the upper side, one in the lower side, are connected to the moving coil, and moving coil is kept on the or wound on the aluminum former. The damping provided is the eddy current damping is used. We have discussed this eddy current damping, and this is produced with the help of the aluminum former. That is the purpose of the aluminum former, to produce the eddy current damping. Damping is nothing but to damp out the oscillations, unnecessary movement of the pointer to and fro. And the control torque is provided with the help of the spring control. There is two springs are used, spring 1 and spring 2. Let us see the diagram. See here, this is the diagram indicating the construction of permanent magnet moving coil. As we discussed in the construction, there are two poles of the permanent magnet, N pole and the S pole. And in between the N pole and S pole, there is the aluminum former. See, this aluminum former is required, as we told you earlier even, that aluminum former is required to produce the eddy current damping. And on that aluminum former, we have kept or we have wound the coil, which is a moving coil. And there are two springs, spring 1, that is a T1, and spring 2, T2. Both are kept on the either end, upper end and lower end of the spindle. And to that spindle we have connected this aluminum former, on which there is a coil and these two springs. And this spindle is provided with the mechanical support with the help of the pivot and jolt bearings, as shown in the diagram. And there is a provision of scale also, a calibrated scale on which we have kept the pointer, and pointer is connected to the spindle. So as the coil will move, the spindle will also move, and as there is a movement of the spindle, there is a movement of the pointer over the calibrated scale. This is a simple constructional diagram. Let us discuss the principle of the operation. This works basically on the principle of motor. What is the working principle of the motor, DC motor? When current carrying conductor is placed in between the magnetic field, it experiences a mechanical force, and that mechanical force produces the torque, and which is in turn rotates the conductor, and conductor is placed on the rotor. Here the rotor is acting as here the aluminum former is acting as a rotor. So let us see the principle of the operation in the detail. When DC supply is given to the moving coil, a DC current flows through the moving coil. When the current carrying coil is kept in the magnetic field, it experiences a force. This force produces a torque and the former rotates. The pointer is attached with the spindle. The former is also attached to the spindle basically. As the pointer is attached to the spindle, when the former rotates, the pointer also moves over the calibrated scale, as shown in the diagram. When the polarity is reversed, a torque is produced in the opposite direction. So in that case, we have to take into account the polarity of the supply. The current direction must not get reversed. If it is getting reversed, then torque produced is also getting reversed. So we will not get the proper deflection of the pointer. So to not happen so, a mechanical stopper is provided. That mechanical stopper doesn't allow the deflection in the opposite direction, deflection of pointer. Therefore, the polarity should be maintained with the PMMC instrument. So the question arises, if we use the AC input, then see, if the AC is supplied, a reversing torque is produced, a pulsating torque. This cannot produce a continuous deflection. Therefore, this instrument cannot be used in the AC quantity measurement. This is a simple working diagram, working principle of the permanent magnet moving coil. As the coil carries the current, a current which is to be measured. So coil is connected to the circuit of which current which is to be measured. As soon as the current start flowing through the coil, we are saying that current carried by the coil, when it is kept in the magnetic field, it produces the mechanical force and in turn the torque, and which is sufficient to rotate the aluminum former, in turn the spindle, and obviously the pointer, as the pointer is connected to the spindle. So depends on the magnitude of the current, the deflection of the pointer gets defined. So it gives the scale, it gives the accurate reading over the calibrated scale. So this is a basic principle of the operation, and in case of the DC, we need to consider, we need to fix for the polarity. If the polarity gets reversed, then the pointer will move in the opposite direction as current direction will get reversed. So to not happen so, we are using a mechanical stopper and will alter or will reverse the polarity so that the pointer will move in the defined direction. Okay. So if we are supplying the AC input, AC has the positive cycle as well as the negative cycle in a one positive half and negative half in a one single cycle. So the torque produced will be of the pulsating in nature. So we will not the deflection of the pointer will be the pulsating in the positive, in the negative, forward and backward, forward and backward. So we shall not get the accurate reading. That's why PMMC instrument is dedicatedly designed for the operation or for the measurement of the DC quantity. Let us see the torque. The magnitude of the torque developed by the PMMC instrument. Let us have the nomenclature. Let TD is the deflecting torque, TC is the controlling torque. We have discussed this deflecting torque, controlling torque. As we know that there are three different torques which are required for the satisfactory operation of the measuring instrument. There is a deflecting torque, controlling torque, and the damping torque. So TD stands for the deflecting torque, TC stands for the controlling torque, theta is the angle of the deflection, K is the spring constant, B is the width of the coil, L is the height of the coil or the length of the coil, capital N stands for the number of the turns, I stands for the current flowing through the coil, and B is the flux density, and A is nothing but the area of the coil. So this is the nomenclature. Just go through this. So moving next, the force produced in the coil is basically given by the expression. We have the standard expression for the force developed due to the coil when it carries the current, that is F is equal to BIL sine of theta. When theta is equal to 90 degree, sine 90 is equal to 1. So basically f is equal to BIL. This is for the single turn. For the n number of the turns, as the coil has certain number of the turns, say this capital N stands for that number of the turns. So for the n number of the turns, f is equal to BIL into capital N. So as we know, the torque developed is nothing but the force into the distance. So TD is equal to force into the perpendicular distance between the force applied and the aluminum former. So TD is equal to, it is nothing but N into B into I into L into the distance is nothing but the breadth of the coil, width of the coil B, and L into B is nothing but the area, length into the width, it is the area. So it is the nothing but N into BIA. Okay. Here they have written B into I into N into A, where B is magnetic flux density, I is the current flowing through the coil, capital N is the number of the turns, and A is the area of the coil. That is the length of the coil into the width of the coil. So here TD is equal to Bani. A simplified word to keep into the memorize it. Bani, again BANI, where B is always a constant, A is the area which is also constant, and N is number of the turns which is also constant. But the current flowing through the coil, it is variable, as we are measuring the current of the circuit where the coil is connected in series. So all these three constants are replaced by the K, P, A and N. So what is the variable? Capital I. So we can write torque developed is directly proportional to the current flowing through the coil. This is the torque equation in case of the permanent magnet moving coil instrument. There is a torque developed is directly proportional to the current flowing through the coil. So what are the advantages of this PMMC? A torque to weight ratio is very high. This is the advantage. Power consumption is less. Scale is uniform. C, as it is directly proportional, so scale is the uniform. Damping is very effective. Damping provided is of the eddy current damping, which is quite useful. Since operating field is very strong, the effect of the stray magnetic field is negligible, as we are using the permanent magnet, and range of the instrument can be extended with the help of the multiplier or shunt connection. We have discussed it in the class. What are the disadvantages? A major disadvantage is that this is the instrument can be used only for the DC measurement, not for the AC measurement. The cost is high. Error is produced due to the aging effect of the permanent magnet. As we are using the magnet, the age gets increases of that permanent magnet, so the magnetic flux gets weakened. So this is the error, and there are also friction and temperature error which are present. So this is all about the permanent magnet moving coil instrument. We shall solve the certain problems numericals on this expression. Thank you for your patient listening.